Okay, welcome back. And we can dive, I think we can dive and go right ahead to the first exercise, structural analysis. In this structural analysis with RSAP, Robot Structural Analysis Professional. So this is the first exercise that we shall be taken into consideration from our reference book, as we said in the introduction. It will be exercise of chapter 2, exercise 18, okay? And what we are asked is to determine the reactions on this particular beam. So I may not have said it in the introduction, but I think it's obvious, it falls to place that structural analysis, not necessarily very deep, but at least the terminologies of structural analysis and stuff like the final element method are things that you should know. Okay, it will be a plus for you to know. I will not say that you will be completely blank or you will not understand anything we are doing if you don't know them, but you should have some fundamentals of strength of materials and structural analysis at least. If you are here, you don't just want to learn the software, right? You want to learn it for a particular purpose. So yeah, that's that. And in case you don't master those courses, um, make sure that when you hear me use terminologies that you don't understand, don't allow yourself to be discouraged and get lost. Okay, we cannot necessarily go right to the ground and grammar of structural analysis. It's not the goal of the course. Okay, it is assumed that you already master those, but if you do not master, have the diligence to take the terminologies that you did not understand and then check them out to see that you're with us, to see that you understand exactly why we are doing what we are doing and what it means, okay? What it means so that you can catch up at any given time. T. Good. Back to the exercise. So the exercise, we have a beam that is trapezoidally. Trapezoidally. Oh my God, that word is always so hard for me. Trapezoidally. Trapezoidally loaded, okay? Uh, Trapezoidally distributed. We have a beam subjected to a trapezoidally distributed load, okay? At point A, the load is of 4 kips per feet, and point B, it is of 8 kips per feet, okay? And the span of the beam is 30 feet, right? So we want to determine the reactions on the beam. The very first thing I would like us to do is to spy the expected answer, okay? What the book gets as answer, analyzing it classically. So we'll go right here. And let's zoom into exercise 218. We have it here, right? So AY, so the reaction following the Y direction at point A will be 80 kips. At point B will be 100. And BX, obviously, the load is, yes, there's no load in the X direction. So obviously BX will be equal to 0. So this is somehow our benchmark, right? So let's go back to the exercise. So this is what we want to model with robot structural analysis, right? So we'll just go back to the software and see how to go about this. Good. So this is the initial interface you will see the moment you launch the software. Robot offers you a number of possible modules, okay, that you can click on depending on the structure that you want to study, okay. So in these cases, for example, it will show me modules that I have recently used, okay, or the modules that I use the most. And you have here 2D frames, which will be for 2D structures that involve stuff like beams and 2D trusses and columns and stuff like that, where you don't need a third dimension in the modeling, right? And here you have building design, you have shell design, etc. 3D frames, okay? If you there are more options. If I click right here on new, you will see more modules here, okay? But again, we'll try to be as specific as possible because we have a lot of exercises ahead of us to be able to explain more, right? So for our case, we are dealing with a 2D structural case, right? It is just a beam, one-dimensional beam. If there was even a 1D possibility here, that's what we would have chosen, okay? So we'll just click right here. And Robo will take us now to the interface where we are able to model, draw the beam, subject it to a load, place the support, etc. And this is the interface right here. So I would like to start by indicating my own teaching approach. It is somehow different. When I'm lecturing on the software, I will not take a lot of time explaining what the different options on the interface are. Okay, so why? Because many times it is new people that watch these videos, and it is useless for me to come and tell you here under file you have this option that helps you to do this, whereas you are not actually seeing the results of what it helps you to do. So we will be touching many of these options, but we will be touching them in time. Okay, so when we have a particular task to do, I will show you this is where you go to in order to accomplish that particular task. In that way, when you have seen where something is located and you have applied it and seen the results for yourself, it stays in your mind very, very easily than for you to just cram the interface. Okay, you will get acquainted with the interface alone as you are using the software. Okay, so that being said, we can continue. So one thing I love about robot structural analysis is the way they've organized what you see right here. Okay, this left side tool, is it left? Right side toolbar. Okay, I love the way they've organized it because they've actually organized it in a way that shows you the progressive steps that you need to follow in the analysis and design of structures. Okay, which is quite cool. You will be seeing that as we are going. It's just one video where I will just show you everything so that you open your eyes to see that, hey, actually that's right, that's what they've done. For now, it's not really essential. So we have a beam to model. Okay, this is what we have. The very first thing that we want to do here is to set up our environment for us to be able to do things right. So we want to make sure that the units, okay, that we are using are actually keeps fit. Okay, so these are imperial units. This is the units from the British gravitational system, right? So to do that, we will go right up here to tools and we will go to job preferences. You see how logical that is, right? We have a job to do in Robo, and to do that job, we need to set the preferences, the conditions under which we want to do the job. And you will see right here the different options, okay? When I click on an option, the details of the options just display right here, okay? So we want units and formats. That's what we want to edit, right? We have two different units here. Is it metric or is it imperial that we want to use? Metrics for dimensions, you have meters, right, as the standard unit, and imperial, you have feet, right? For mass, you will have kilograms on metrics, and you will have slugs at the level of imperial. For force, you will have Newton or kilonewton, Newton at the level of metric, and kips, pounds at the level of imperial. Okay, so what we want to use here is imperial units. But if you are not convinced, there is a plus right here where you can see the details of what we are talking about. Okay, so it details them into different categories of units, right? So we have dimensions. When it comes to dimensions, that means measuring things like the length, the breadth, the thickness. Those are dimensions, right? So the diameter, the radius, etc. Those are dimensions. So here we have the first option, structure dimensions, and we see that because we've chosen imperial, it is in feet. When we say structural dimensions, it is dimensions that generally measure, for example, the different structural elements of a structure. So in our case, it will be the length of a beam. Here, for example, this 30 feet here is a structural dimension, as opposed, for example, to what they show under, which is section dimensions. Section dimensions now is, we suppose, for example, that this beam is an I-shaped beam, right? Then the I-shaped beam will have a particular thickness for the flange, okay? That thickness is a section dimension. it will have a particular thickness for the web. The web is a section dimension. Okay, it has a particular overall height, a particular overall breadth. Those are section dimensions because they are dimensions of the sections of the elements. Okay, so those dimensions are generally relatively small, right? To structural dimensions. So we express them in inches so that we can manipulate them easily, right? But I digress, right? The structural dimensions here would be enough for this particular example. So let's check for forces now. We need to make sure that the forces are in kip, right? They are in kilopounds. That's what we want to use. So that's good. The precision right here, yeah, we can leave that precision, right? When you see this E here, it stands for precision. If where we are now, it says it will express all the forces in with two decimal points, okay? Two decimal numbers. So if I reduce that here, then it's one decimal now. If I do this, then now a whole number, okay? And but let's leave it by default to two decimal points, okay? So once we are done, we can just come right here and click on OK. So again, for job preferences, you can choose material preferences and see the options. Is my robot okay? Okay, good. You can see material and see the options. So this falls more on design, okay? So don't worry, we'll have time, a lot of exercises and more series to be able to browse through that. So let's just go ahead and to okay. Good. So here we are. What next? The next thing we want to do is actually to draw our beam, right? Right. So to draw a beam or a column, since we're dealing with 2D frames here, we just need to come right here and select bar. Okay, so this is what I'll be using for now. Just focus. We just need to come right here and select bar. The moment we select bar, you have this particular window that pops up. The goal of this window is for you to describe the type of bar that you want to draw first. Okay, what is the type of bar? What is the section of that bar? Of which material is that bar made up of? Okay, and then you can draw your bar so that you have the exact bar that you need. But again, for the bar type, we are just doing normal structural analysis here, and all we need to know are the reactions. Okay, so we are not even in the element per se. So we would take a simple bar. Okay, simple bar can be a beam or a column, it doesn't matter. Okay, and here at the level of section, we don't really care about the section, right? Because we are not evaluating stresses or strain just yet, and we are not designing anything just yet, okay? So we'll leave that for now. The material too is not important, okay? In this particular scenario, no matter the section, no matter the material, it will give us the correct answer, right? So what we want to do now is just to draw. Good. So, one thing I did not say, sorry about that, is that, which I should say even if I am not presenting the interface, is that this right here, this blue area, is your drawing area. This is where you represent your structure. This is where you draw your structure. So if it is the beam that we are drawing now, this is where we will draw the beam with the loadings, with the supports, and everything. And this is where we shall even be seeing diagrams like moment diagrams, shear force diagrams, normal force. This is where we shall be having our structure graphically observed. Okay, to be sure that we are doing the right thing at any given time t. Good. So that being said, we can go right ahead and draw our bar there, right? So look at this. The moment I open this window, when I'm navigating my mouse, you'll see that there is a cross that has appeared, right? You're seeing that cross together with me, right? If I close this, the mouse is just normal, it's just an arrow. But then when I open this, okay, and I navigate away from this rectangle, right? You see that it is a cross that appears. So this shows me that I am in bar drawing mode, okay? So a bar, which is the beam that we want to draw, is delimited by 2 points, right? We have point A and point B. And point A is 30 feet away from point B. That's all we need to know here, okay? So if I take point A to be this, look at, as I'm navigating, okay, the coordinates here of the point where I'm about to click is changing. and that's the way I can measure my 30 feet. So if I come, for example, here and I choose, let me start with the point 0. Okay, this is it here, 0, 0, right? So at 0, 0, when I click there, right, I have clicked on the first point. So look at what has happened right here. As I clicked, it moved from the first point right to the second point. It has stored the coordinate of the first point, and now I'm ready to draw the second point. And you can see that wherever I'm moving now, there is a line that is following my mouse, right? A way of saying, wherever I click on the second point, a line will be drawn to show the final structure, right? To show the final beam that I wanted to draw. So if I've said here is 0, then all I need to do is what? Move 30 feet away, right? You can see that on the coordinates at the level of n there, right? So now it is 30, comma 0. As I click there, that is it. This is my beam right here that has been drawn. Okay, so just to show you some things to motivate you for future for future video. This video, sorry, I can actually come here and we can see the section of this beam. Okay, are you seeing here? It is to show some displays. Okay, some displays. Yeah, displays. Yes, displays. Good. So I can come right here to this navigating board that enables me to see my structure from different angles. And if I click on home here, for example, you can see the 3D beam, right? You can see that it's an eye steel beam. Okay, I can rotate and see it differently. So this is to tell you, when you see us drawing lines in structural analysis and stuff like that, you should understand that these are the kind of things that those lines represent. It is not just lines to draw lines per se, right? Good. So we want to come back to we were at the level of the XZ plane, right? So we want to come back to the XZ plane at y equals 0, right? That's where we are. Don't worry, the details of this, we have a lot of exercises to show you all of that. Okay, good. That being said, we can deactivate the section now to be able to continue. So this is our line, and this point here will represent our point A, and right here will represent our point B. So going back, what's the next thing we want to represent? Oh, maybe the loading, right? Maybe the loading, the trapezoidal load, right? So for that, you will need to come right here and define a particular load type first, because structural analysis, we may just define loads and use them for the sake of the way they are. But in reality, when you're dealing with real structures, you have different types of loads. You have dead loads, which speaks of loads that are permanent in their position throughout the lifespan of a particular structure. You have live loads that can vary in magnitude or position throughout the lifespan of the structure. You have wind loads, which is technically a kind of live load also, but has its own specific way of dealing with. You have snow loads and earthquake loads, right? You have different kinds of loads. And when you are dealing with the software, professional software like Robo intended to design real structures, you have to indicate the types of loads that you are dealing with. So that's why that's the very first option here. Okay, you come right here to load type, and you see the nature here, right? You can choose live, wind, snow, or seismic, okay, which is earthquake loads. So we will choose dead load because we suppose that that load will always be there, right? But that's not the real reason. Even if we choose live load here, in fact, the truth is, for now, it doesn't really matter. Okay, so but you have to define the type of load, and you just click on add here. Uh, Before I do that, I want to show you something. In reality, this is where we are supposed to define the load. Are you seeing that? When I put my mouse there, it is load definition. But right now, it is inaccessible. Okay, I can't access that because I need to define the type of load that I want to define a load under. Okay, so now when I click on add right here, it adds a load here, and you can see that this load definition has been enabled. Okay, because every load I will define here will be considered one, will be considered a dead load, as you can see also right here. Okay, so I'll click here. Okay, Now, what do we want? We have nodes. Nodes here speaks of loads that are applied on nodes. It can be a point moment, it can be a point load, etc. Right? And you have bars. Bar speaks of uniformly distributed loads, uniformly distributed moments, linearly distributed loads. In fact, distributed loads in general, or point loads that you want to point loads or point moments that you want to apply at a particular distance in a bar without necessarily creating a node, a different node to define a new bar. You will get to understand as we are going, okay? So what we want is trapezoidal distributed load, right? Look at this here. Trapezoidal load, right? This is what we want. And Robo shows you all these options. It's very difficult. It's very, wow, what was I about to say? Difficult? God. It's very easy to decode this, right? All you need to do is just to look at the image right here and it tells you everything. Okay, the image tells you everything. So here, for example, we say direction of load action, Z. I think that's correct, right? If we look at our axis here, the Z is pointing upwards and our load here is pointing downwards, but it is in the Z direction in Robo, right? So the positive Z direction is upwards, but our load is pointing downwards. It means no matter the magnitude of the load that we are indicating, we have to put a minus in front of it because forces are vectors, right? A minus to indicate that the load is pointing in the opposite direction than the default positive one, right? Good. So, what is the magnitude of P1 in our case here? The magnitude of P1 for our exercise will be 4 kips per feet, right? And P2 will be 8 kips per feet. So we just come right here and indicate -4 in our case so that it should point downwards, and P2 -8, right? Good. Now, at this level here, you see there's a distance x1, there's a distance x2. This is to indicate where do we want the trapezoidal load to be applied. Do we want it on all of the bar or do we want it on a specific part of the bar? Okay? When I say bar here, I mean beam. I hope you understand that. So, we have two possibilities. It is either relative or it is absolute. Okay? So, for this video, we'll take time to explain what relative and absolute stand for. But for this video, let's use absolute relative and let me try to explain what that stands for. Relative somehow does it does an interpolation of whatsoever the length of a particular element may be. It interpolates it to the beginning of the element being equals to 0 and the end of the element, which is any given L, being equals to 1. So for this bar, for example, okay, the beginning here will be 0 and the end here will be 1. Okay, and any given distance in the middle varies between 0 and 1. Okay, I don't know if that's clear, but it will become clearer. A way of saying that here, for example, we want the distance x1 to be equals to 0, right? Because the distance x1 is measured from the origin right up to the initial point of application of the trapezoidal load. So we want it to be 0 because we want the load to start at the beginning. So we don't want any distance here. Now, where does the second point of application of the trapezoidal load start? Okay, it starts at the level of x2 and x2 is measured from the origin. We want it to span how? We want it to span throughout the beam, right? We want this second point load to appear here at this point. So we will give it a distance of 1 because in relative, okay, the overall length of the beam is measured as 1. Okay, we are in a kind of normalized reference system. Okay, good. That being said, yes, we want a global coordinate system. Global again and local is something that we will explain as we are going. Okay, good. So we will add that. So as we have added, all we need to do is to go right here and select where we want to apply it. Now, this is a little bit complex. Look at this. If I click right now, have you seen that? This is not what we want, right? It's supposed to start with the small this way, the 4 keeps this way, and then the 8 this other way. Are you seeing that? So, but if I click here, then we have the result that we want. A moment. Has it cancelled that load? Good. If I click here, then we have the result that we want. Right? So what transpired? What just happened? Well, the secret is watching the arrows. Look at these arrows here. Are you seeing this arrow here and this these two blue arrows? Look at the direction they are pointing. Okay, the two arrows when you're selecting a particular element will always point from the first to the second node. Okay, so when I move here and I cross the middle, it is now the opposite direction. So if I click in this position, Robo understands that this is the first and that the second node is the other way. If I click in this position, Robo understands that this way is the first node and the second is the other way, right? But we want P1 to be applied where? On the first node this way, okay, and then to the other way. So this is the way we have to click. Okay, so let me select that again. Oh, what's happening? Apply, apply. Something wrong somewhere. Okay, let's add that and then apply. What's happening, Robo? These guys are not behaving. Okay, let's just do that. Wow, many things have changed here. Something went wrong somewhere. Oh my God, I pressed Control Z several times and it seems as it has cancelled a lot of things, but it's okay. It's okay, okay. So don't worry. Let's just go ahead and add that load real quick. You see that it cancelled the load that we added and close. Okay, so from all indices, it has already applied the load, uh, but I want to be sure, okay? I want to be sure, so I'll go right ahead to the load table and see because I clicked a lot of times. I don't know if it has applied that load several times or whether, okay, good. It applied it just once, but let's go ahead and apply it again ourselves, okay? Good. So what do we do? What do we do? What do we do? We go to load definition. We choose the bar option. We take trapezoidal distributed. It's already defined. We thank God. So we will select that and we will go right here and add. So that's what we have. This is where we add, right? So the options right here are very useful. Okay. So you see that the moment I close the load definition, right? The load definition window, okay, the load itself disappears. We don't want that from time to time. Okay, if you want to see the load without necessarily clicking on the load definition, you can always come here, okay, and click on loads and you will see the load here. And if you want to see the values, you can click right here, okay, on load value description, and you will see pz is equals to -4 -8. Okay, so that gives you, it gives you the load here and the load here. Perfect. Um, um, yeah, I think we are good to go. Okay, so you can always have an inventory of the loads that you have applied by simply coming here on loads and going right to load tables. Okay, load table will show you all of the loads that you have applied on the different elements. It's a kind of tabulated list of loads, right? Good. Look at this. Oh, I've just added a new load by mistake. So when I want to cancel the load here, I will just select the line. You see that? Select the row concern and press Control X, and that should disappear. You will see that on our beam we have two loads. Okay, because again this is a real project, by default whenever you create a particular element, there is already the moment you add a dead load, there is already a default load that comes with the dead load, which is a self weight of the particular element. Okay, Robo automatically calculates that according to the material that the element is made up of and the cross section that you have chosen for that element. Okay, so but in this case structural analysis we don't want the self weight, so we'll select it and press Ctrl X so that we are sure that we have just our trapezoidal load that we defined initially. Okay, good. So once you finish inspecting this list, you can always come right here and close so that you are back to your main structure. Good. So we finished with the load. That was quite long. What next do we have? We need to model the supports, right? So we have a roller support at A and we have a pin support at B. So let's go ahead and model that. For support, it's obvious right now, right? When you look here, this it tells you everything, okay? These are the supports here. And I'm sure by now you are already getting the feel of the robot modeling style, okay? You always click on stuff, a particular window pops up for that particular option, and then you relate with that window together with the drawing area to model your structure and see some stuff. It's really cool. It's really cool. Good. So this is what we are having. We have a pin support, right? The pin support is supposed to be applied where? At the level of node 2, right? So I'll just go right ahead. I hope you see what I did. This is the list of available supports. You select one, the one that you want. You make sure that, sorry about that. Wow. Okay, so you make sure that that's what is selected. Okay, that is what is chosen by default. Sorry, the black arrow is right there. Okay, and then you just come to the drawing area and choose the node where you want to apply it. So if I select there, you see my small triangle right there that shows me that that is the support I've chosen. Now, on this other node 1, it is supposed to be a roller support, but I'm not seeing any roller support defined here. Okay, so I can define a new support all by myself. That's by simply clicking here on new support, okay, and blocking the particular degrees of freedom that will not be relevant. Okay, so here let me give a label. The label here can be anything you want, okay? Feel inspired. So I'll just say roller Z because it's supposed to block the Z direction, right? These are the things that I'm saying you have to have a background in strength of materials and structural analysis. Okay, so we want to tick here the directions that it's supposed to block. Okay, so which it should allow for rotation, it should allow for movement in the X direction. Okay, but it should block movement in the Z direction. That's a roller support. It blocks displacement in only one direction. Okay, so I will add that and then close, and right here I should have a roller now. Okay, so it is selected. I can come here and then choose node 1, and that's my structure, right? That's it overall, okay? So you can also be sure of the dimension that you've chosen. If you come right here to tools and you choose on dimension line and you select right here, you can measure the distances, excuse me. So we want the distance from this node to this node. What is it? Okay, so you see that it's 30. So somehow we have drawn on Robo the exact exercise, right? The exact exercise, and we know the units. We know that we have chosen the imperial unit system. Okay, so let me just delete this, and then what next after you've drawn? It's good to draw, it's good to draw, but how do we determine the reactions? Okay, well, once you have modeled in Robo, that's the most exciting thing. The rest is just to click on the button, all the calculation is being done, and you just observe your results, right? So I'll click on the button, which is this one. I'm really sorry for the noise behind me. Wow, it's alarming. I'm really sorry. I'm at a window on the roadside and it's not very easy. Okay, but it's a passing by noise, okay? It will be done in no time. Good. So the moment you're done is just to click right here. Okay, just click on calculations and Robo will perform its magic using the finite element method, rigid, robust algorithm that has been programmed in the background and will get us those reactions in no time, right? So everything now has been calculated. When you come right here and you see it green, it tells you that the results are what? Available. Okay, if you see this orange, it should tell you that your results are outdated. But again, these are things that we will see as we are moving along. Okay, to check the results, we'll go right here to results and I'll click on diagrams for bars. Okay, don't be surprised. I will have clicked on reactions here, but it will show us a particular table. Okay, let's just click there and see where we can already see the results, right? Remember, we had 80 for A, right? And then 100. So you see This 1 1 here stands for the load case. This one, right? The load case here is case 1. We are working with this for the dead load because everything we modeled was under the dead load, okay? That's why you see 1 1 here. But here are the nodes, okay? So if I go back, here, what will you see? Let me try to display nodes here and just try to zoom, or let me remove the support. I can remove the supports by clicking here. I can remove the loads by clicking here, okay? So you'll see that here, robot sees it. What you are calling A, robot sees as node 1. What you are calling B, robot sees as node 2, okay? So when you come to this reaction table, where is it? Where is it? Okay, let me put it up. Good. So you see that here node 1 is 80 kips, that's the reaction, and node 2 is 100 kips, that's the reaction, which is the exact answer. I don't care about what is down here for now. These are our answers up, which is the exact answer that we got from the textbook. You remember, right? So let me try to show that graphically, okay? So graphically, it will look something like this. We will go to results and diagrams for bars, and then we will go to the reactions part, okay? And we want to see the reaction following Z, and why not following X, okay? And if I click on apply there, what you will see is just 2 lines, right? But we are not seeing their values. So you have to click on description here and apply to be able to see the value. So you see that the reaction at point A is 80 facing upwards and here 100. So to make it beautiful, we can put our supports back, we can put our load back, and everything is fine, right? So this is our structure and these are the reactions. So again, to confirm that at A we have 80 and at B we have 100, we can always come back here and at the level of answers 218, that's exactly what we had, right? At AY was 80 and BY was 100. So I hope this gave some fundamentals. Again, this is not necessarily a robot course per se. We are doing what we can with the help of exercises. Okay, so it's a project-oriented course. So I'll be putting some links in the description to help you actually go and see some tutorials that may take you through the course systematically. Okay, level by level. So I hope this helps and. I will see you in the next video for the next exercise. Bye bye.